All right, guys, so in this section, we are going to talk a bit about more of a context description of what an integral does for us. And for differential calculus, the underlying question was finding or studying the equation of a tangent line to a curve. For integral calculus now, the fundamental underlying question is going to be what is the area under the curve? Now, we know that if we have a basic geometric shape, most of the time we have a basic geometric formula that can give us that area. But if we have a really unique area, a unique region, then we're not going to have a formula for that. So we're going to have to come up with a way to figure it out. Now, fortunately, the area of a rectangle is very simple, right? Area of a rectangle is very simple, base times height. So if we have a region that's not very standard, what we're going to do is ultimately construct infinitely many rectangles in that region, compute the individual areas, and then add everything up to get the total area. Now that sounds like a lot. That sounds like a big process, and it is. It's the entire section of 5.1 and the entire section of 5.2. So just kind of hang in there. Let me get some stuff up on the screen here as we work this first example. I don't normally work examples straight out of the textbook because I wanted them to serve as additional problems for you to have as resources. But because this is such a visual type of section, the problem that I have in us finding the area above the x-axis below that function on this interval is from the text on page 248. So I would encourage you, as I try my best to draw these pictures, I would encourage you to look in the text at their pictures as well to get a better idea of what it is we're doing. Okay, so let's kind of start over here. We're going to find the area above the x-axis below this function on this interval, and we're estimating with finite sums. If we had infinite sums, it would be an actual number, but instead, since it's finite, we are only estimating. We're coming up with the approximate value. Now we're going to actually do this, I believe, 4 or 5 different ways. And so the first way is we're just going to use 2 rectangles. Now you can imagine the fewer number of rectangles you have, the less accurate your estimate's going to be. If we can have more rectangles, the better. But we're going to start off with 2 to get started. Okay, so real quick, just so everybody's on the same page, that function f, that's going to be the parabola that's upside down, shifted up 1 unit. And if we're on 0 to 1, this is what we're looking at right here. Okay, that x-intercept is at 1. So I'm going to draw that a little differently over on the other side of the screen, but I just wanted to review that with everybody. So let me take that off. So this is what I'm looking at here. And I'm going to try to draw this as big as I can and make it as clear as possible. But again, look in your book at their pictures. So we've got here this parabola, the vertex of it's at +1, and we know that it's going to come down like this and then continue down. But either way, that's at 1. So now to start, we're going to construct 2 rectangles. And so if we're going to construct 2 rectangles, halfway between 0 and 1 would be right here at our 1/2. So here's our 1/2. And my first rectangle that I'm going to construct is going to look like this, where I come straight out and down and meet up with that 1/2. Okay? The second rectangle that I draw is going to be this guy right here. And all right, now, no doubt you can see that the area under the blue rectangles is not the same as the area under the black curve. Remember, this is an estimate. I would need infinitely many rectangles to accomplish my goal of finding the actual area. But using 2, this is what we have. Now for the area of these 2 rectangles, we know that the area is going to be a base times a height. Okay, base times a height. Well, the base in both of these is the same. Okay, the base is going to be 1/2. If this is the rectangle that I'm studying, it's got a base of 1/2. I would just need to figure out the height now, right? Well, the height is actually going to be this guy up here. And if you'll notice, that guy up there, that's going to be our function at 0. So this guy here is f of 0, right? If I plug a 0 into my function, it's going to spit out the height of my function. So that's going to be f of 0. So for my first rectangle, I've got a base of 1/2 and a height of f of 0. So far, I've got a base of 1/2, a height of f of 0 for my first rectangle, plus the area of my second. Well, the area of my second rectangle, the base would still be a 1/2. And now the height of this rectangle would be my function evaluated at 1/2. So this guy right here, that's going to be f of 1/2. Okay, so my f of 1/2, there we go, there's my height. Now, once I compute this, that's going to give me my approximate area. But again, just to summarize, this is the area of the first rectangle, base times height, plus the area of the second rectangle, base times height. So when I evaluate these, f of 0 equals 1, thank goodness, right? Because we know that that's 1 up there. So if I plug a 0 in, it spits out a 1. And then for the next one, f of 1/2 will leave us with 3/4. So again, f of 1/2, go to the function f, plug in the 1/2, it spits out a 3/4. So when we run these numbers now with a calculator, this is going to give us a 0.875. So we've got an approximate area of 0.875 using two rectangles. Now, I'm going to address this again here in the next part, but keep in mind, this looks to be visually an overestimate, and it is. So you'll see the text refer to this as an upper sum. We'll look at the lower sum in the next example, but for now, I'll let this be. I'll go ahead and clear the screen, at least what I need to clear, and then we'll come back and we'll look at another approach to this. Okay, so we're going to look at the same problem here, and instead of using the upper sum, we're going to use the lower sum. Some of you might have had a thought in your mind when I drew those first couple rectangles that, well, there's another option for this, and there certainly is. So if I go ahead now and I construct two more rectangles, but just in a different fashion. For example, this guy right here could be a rectangle. And my second one, this is where it's very difficult for me to draw, so you'll want to rely on looking at your book. In particular, page 250's got something similar to what I'm trying to draw here. So there's that first one. You see how it starts and comes up right here and then comes over, as opposed to coming here and going across like my first one. Well, my second rectangle would actually be from here just straight across to there. And I know that seems strange, but that's my second rectangle right there. And that is clearly now an underestimate, or which will be our lower sum. Okay, now we're going to do the same thing we did just a few minutes ago. We know that area of the two rectangles is going to need a base and a height. For the first one, our base is that, and our height would be this f of 1/2 right here. So f of 1/2. And then the second one, we would have a base of 1/2 as well, but notice what our height would be. It doesn't look like I have any height, does it? And so you're right, because at this point right here, at that point, now we're at f of 1, f of 1. And at f of 1, if I plug that in, isn't that at 0? Yep. And so this guy is nothing more than the 1/2 times the 3/4 plus the 1/2 times the 0. That's going to give us a final answer of 0.375. So this guy is a big underestimate of the actual area. We call this the lower sum. And it's because you've got a lower sum and an upper sum, that overall area is going to be somewhere between those two things. So 0.375 to 0.875. So that's using two rectangles and an upper sum and a lower sum. So hopefully you're getting a better feel for how these rectangles can be constructed. I'm going to take it a step further, knowing that there's probably some questions. I want to do another iteration, we're going to do 4 rectangles now of an upper sum and a lower sum, and hopefully by the end of that, I think it'll hopefully make a little more sense.